Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The oxylyl cation is a 1,3-dipolar species, or zwitterion, with a positive charge on carbon and a negative charge on oxygen. In this molecule, the oxylyl cation is tethered to a cyclohexane ring with an adjacent OMe group. The rearrangement involves intramolecular electrocyclic ring closure or 1,3-dipolar cyclization. Moving on to the next step. Identify the reactive species. The starting material is an oxylyl cation where there is a carbocation at C1 of the cyclohexane ring and an oxyanion, enolate like oxygen, on the exocyclic is equal to CH2 group. This is effectively a trimethylene type zwitterion or an oxylyl dipole C+, C is equal to CH2 with O on the terminal carbon, i.e., the system is plus Cc is equal to CH2O. Moving on to the next step. The oxylyl cation 1,3 zwitterion with C+ and O undergoes intramolecular ring closure. The negatively charged oxygen, O, attacks the positively charged carbon, C+, on the ring. Since these two charged centers are 1,3 related, separated by one carbon bearing the exocyclic methylene, their combination forms a three-membered ring. The C+ is at C1 of cyclohexane, and O is on the carbon alpha to C1, the exocyclic carbon. Ring closure between C+ and O gives a three-membered ring containing oxygen. But that would give an epoxide-type structure. And for the final step, re-examining the connectivity. The oxylyl cation has the structure, ring C+, positive, connected to C is equal to CH2 with O negative on that same carbon. The 1,3 relationship is C+, ring carbon, C, exocyclic, O. Intramolecular combination of C+ and O closes to form a three-membered ring, a cyclopropanone. The C+ attacks the O or the O attacks C+, forming a CO bond in a three-membered ring. However, if the bond forms between C+ and O, and the exocyclic carbon is between them with A is equal to CH2, the product would be a cyclopropanone, cyclopropane ring with a ketone C is equal to O. Actually, the correct interpretation of the oxylyl cation rearrangement is well known in organic chemistry. An oxylyl cation, 2-oxidoylyl or trimethylene methane oxide, undergoes this rotatory electrocyclic ring closure to give a cyclopropanone. The C1 plus C is equal to CH2O dash system closes to form a cyclopropanone ring where the C1 of cyclohexane and the O bond together, giving a spirocyclopropanone fused at C1 of cyclohexane, with the OMe group remaining at C2. A cyclohexane ring with a cyclopropanone, three-membered carbocyclic ring bearing C is equal to O, attached at C1 and OMe at C2. Why other options fail? A. Shows a methylene-cyclopropane product, no oxygen incorporation into ring, which would require a different rearrangement pathway. B. Shows an epoxide, which would require O attacking an adjacent CH or forming a two-membered ring closure that doesn't fit the geometry. D. Shows an aromatic ring, implying aromatization occurred, which is not a simple rearrangement of the oxylyl cation under these conditions. Therefore, the correct answer is C. Therefore, the correct answer is option C.